Well, we're back, sort of. It's been 15 months, 16 months since we last came to the rooms, and we have our allowed 6 people in the rooms, suitably spaced out, so to speak. It's really nice to be back, but obviously we would have loved a fuller room. It all looks like we've all got the lurgy and we're staying apart from one another. But anyway, we're here. Now, this is thanks to Dave and various others to get us up and running with the Zoom. It's going to be recorded, so if anybody misses Jens's presentation, then it should still be available. Anyway, Jens was very keen to do this to an audience, and I don't blame him, having given a few talks over Zoom myself. It's a much preferred way because you do get a degree of audience reaction. Hopefully we'll be all back before too long, but after Boris's announcement today, of course, it may not be quite as soon as we hoped. But we'll work on the next meeting, which will be the 12th of July, which will be me giving a talk. Now you see me, now you don't, but it may be on Zoom, so we'll let you know one way or the other. We'll have a discussion about this later. We have high hopes for the Perseids on the 12th of August. Again, an email will go out about that. And then in September, we have a hope, we really do hope we can get back to normal meetings. That will obviously dependent on government guidelines. So anyway, I will now hand over to Jens. Jens is a popular talker at this venue, and he's given us a lot of thought-provoking talks over the years on a variety of subjects, relativity, etc., and Arecibo quite recently. This is going to be even more intriguing. Tonight he's going to talk to us about infinity. So I hand over to Jens.
Thanks for the introduction. I hope you see the infinity sign on the screen. I'm acutely aware that some of my previous presentations have been described as challenging. This is a different league. It will be even more challenging. I assume that most, probably all of you, are a bit confused about the whole concept of infinity. I promise at the end of the talk, you'll still be confused, but your confusion will be at a much higher level. Here we go. So infinity in mathematics is closely related to mathematical logic. And the way I'm trying to do it is to do it largely chronologically. So go through how the concept has evolved and what is included. So the main sections of the talk are here. Start from some basic examples of how we use the concept of infinity in sort of almost daily life. But it wasn't formalized for a long time until Georg Cantor came along and introduced set theory and infinity, and really got infinity on a more theoretical footing. One of his admirers was the German mathematician Hilbert, and Hilbert has given name to Hilbert's Hotel, and also he's well known outside mathematical circles for his list of problems. Frege and Russell started to make the relation between logic and mathematics, and we got axiomatic set theory, which was really the formalization of Cantor's work. And then we go to Gödel and the incompleteness theorems. And I'll give some example of large numbers and make some final comments and also raise a few questions. I will probably recommend that I'm allowed to do a break after the third section, and then you can relax and rest your head for a while and then come back for more if you like, or stay away. Okay, just some terminology. I try to define some terms, and they're shown in red here. Terminology for numbers. Well, we have the counting numbers. That's the position in a sequence. For example, the 5th person in this room, or whatever, the 5th banana on the tree. So that's counting numbers. They're also known as the ordinal numbers. And we have another type of number. Usually we don't distinguish too much between them, but here we do have to. And mass numbers. So it's the number of elements in a set or in a group. So you can have the number of people in this room is 6. So if you have a set with 5 elements, we have the mass number 5. It's also called the cardinal number. So we have sets of numbers, and you may have seen these before. We have the natural numbers, 1, 2, 3, 4, 5, 6, etc., usually called just n. We can include 0 and the negative numbers, and then we get the integers. We can include fractions, and we get to the rational numbers. And we can take all the real numbers that include radicals, for example, square root 2, or transcendentals like pi that can't be written as a radical. And we can also form subsets of numbers. For example, the even numbers constitute a subset of the natural numbers. The primes is another subset, and the squares is another subset. We can start to make sums with an infinite number of terms. For example, the harmonic series. The summation sign means that we let I take on all the values from 1 to infinity, and then we do the sum. But this one diverges. Whatever large number you give me, I can find a number of terms that will sum up to something larger than the number you gave me. So this one doesn't have a fixed result. Even if you take the inverse of the primes, that also diverges. A lot slower, but it still diverges. It will go to infinity. However, if you take something like the inverse powers of 2, if you add them all up, you'll get 1. Every time you add half of what you're missing to get to the 1. So that converges. And there are all sorts of sums like this with an infinite number of terms. Quite a famous one here is the inverse squares. This is known as the Basel problem and was solved by Euler. I don't know if you know the result, but to some surprise, it contains pi. What on earth has this got to do with circles? But it does. And one of the proofs of this sum is using that fact that there is a relation to a circle. So you have an infinite number of terms, but a finite sum. And there are lots of examples like this. So this is a use of infinity, and we don't really think too much about what we really mean by infinity. It's just something very big. We can also do calculus. We can integrate to infinity. And here's a quite famous example. We have a solid here, or kind of a trumpet, and the surface is defined as 1 divided by x, the position on the x-axis, and it goes from some point A to some point B, and there's a mathematical expression for the area of the surface, and it looks like this. If we just look at the first term, the square root there is just to take into account the fact that the surface is curved. We can, if we drop that, we know that the first term is certainly bigger than what we get if we drop that 1 divided by x to the 4th power. And we get an integral from a to b of 1 divided by x, which is known as the log. So the area is 2 pi times the log to the ratio of the 2 points. We can also find the volume. It's another integration from a to b, but now it's 1 divided by x squared. And the pi x squared is the area at a certain point, and then we just integrate that from A to B. And the funny thing is that if we now let A equal 1, and we let B tend towards infinity, the area will diverge. But the volume is finite. The volume is pi in this case. And the way it's put is that you can take this thing, you can fill it with paint, but you can't paint the surface, which sounds like a contradiction, but it's actually correct. First time I came across this one was in a mock exam for A-levels in math. Nearly everybody could do it. The calculation is not very difficult. Actually, it was a slightly simplified version we got. And quite a few wrote in their paper, this can't be right, but I can't see any mistakes. So I'm submitting it anyway. But there is no mistake, it is right. And you can have the analogous example, you can have an infinitely long curve that occupies a finite area on a plane. So when you go, when you change dimension, you can go to something that's finite to something that's infinite, or vice versa, depending on what direction you go. So this is another example of use of infinity and some apparent paradox. We use infinity in physics. For example, when you define potential energy, it's relative to infinity. If we have two masses, we have the gravitational force between them, and the potential energy at a distance is the energy gained by moving that particle or planet or galaxy, for that matter, from a certain distance d to infinity, which is the reference point. And if you do the math, and you've got to be a little bit careful with the signs, and it comes out as a negative number because when you go from infinity to a certain distance, you have lost energy, and it requires energy to bring it back to infinity. But the main point I'm making here is that we use the concept of infinity without really thinking too much about it, just convenient reference point. Okay, this was all used by mathematicians and physicists for probably a couple of centuries without thinking too much about what was going on. And then along comes Georg Cantor and proposed that we should use the concept of sets as the basis for mathematics, working together with another German mathematician, Richard Dedekind. And he wrote about this in numerous papers. A set, in a mathematical sense, is a collection of elements, whatever, apples, cars, persons, or numbers, in particular numbers, of course. And an element in a set can itself be a set. So you can have nested sets. Set can be finite or it can be infinite. For example, the set of people in this room is certainly finite. The set of natural numbers is infinite, but it's countable. We can put them in a sequence and we can map them onto the natural numbers. So we call them countable. And then we have some notation here. The infinite ordinal number is denoted omega. And all sets that can be brought into a one-to-one correspondence with the natural numbers, they're called equinumerous, and they are countable. And they all have the same cardinality, which is infinite, but it's still defined. And it's denoted by the first letter in the Hebrew alphabet. There's a reason for that, why it's the first, but I'll come back to that. And now we can do some examples. We have infinite but countable sets. For example, the even numbers, they can be brought into a one-to-one correspondence with the natural numbers because we have the first, the second, the third, etc., etc. The primes, the same thing. We have the first prime, the second prime, the third prime. The squares, we can take the Fibonacci numbers. We start with 2 ones, and then each subsequent number is the sum of the 2 that precedes it. That's another subset. Powers of 2, or the factorials. You can go on and form these subsets. And they're all countable because of this one-to-one correspondence with the natural numbers. So although they're subsets, and you think there are fewer of them, they still have the same cardinality. They can be mapped. You can pair them off with the natural numbers. So they're you can say they're equally infinite. So what happens if we now, just some properties of this cardinality here. I'll just, because it's not really a number in the usual sense. So you can't really do calculations with it, but well, we do it anyway, but it's not obeying the usual rules. If you add 1 to infinity, you still have infinity. If you add 2, or if you add some number, some natural number, you still have infinity. Even if you multiply, you still have infinity. Or if you square or raise to some finite power, it's still the same cardinality. So how about the rational numbers? Now, intuitively, you would have thought that the rational numbers is a much bigger set than the natural numbers, more infinite. But here's the clever bit Cantor came up with. If you arrange all the rational numbers in this table here, and then you take a walk around it, you will pass through all the rational numbers, and you compare them off against the natural numbers. So the rational numbers and the rational numbers and the natural numbers are in a one-to-one correspondence. They're equally infinite. They have the same cardinality, which is a bit puzzling, but that's how it is. So how about taking all the real numbers? Imagine the real numbers, assume they had the same cardinality as the natural numbers. Then you could put them on a list. The list would be infinitely long, but it would be countable. You could pair it off. So assume you could do that. We write the numbers in binary form just for convenience. So you have a number of them here, you put them in some random sequence. And this list is infinitely long. But is it complete? Well, this is Cantor's argument. If we now form a new number, we take the first row and change the first digit and go on like this. So for each new number, we choose the other one. And we will now get a new number, which is definitely different from all the numbers on the list. You can see that the new number I formed, apart from the first decimal place, it's exactly the same as the first I wrote, but it's not the same because I changed the first digit. So the new number I formed is not on the list. Therefore, the list, even if it's infinitely long, couldn't have been complete. And therefore, the original list is too short. So the real numbers has a higher cardinality than the natural numbers. In some sense, it's more infinite, there are more of them. And this is known as Cantor's diagonal argument. You can see from this table how he went about it. The real numbers, they represent points on a line, and they're said to form the continuum, and that's denoted C. And the fact that the cardinality of the real numbers exceeds that of the natural numbers can be written like C is larger than LF0. And because I wrote them in binary form, we have a very simple relation, which is a bit strange because I now say C equals to 2 raised to Aleph. Aleph naught. Maybe I should just go back if I can. You can see from this table, it's clear in binary form that you have an infinite number on each line, and the number of possibilities you have for each position is 2, either 0 or 1. And so the number of different combinations you can have is 2 raised to the number you have on the line, which is Aleph naught. So the total set of real numbers is just this relation here, which is a bit strange when you first see it. That there is this relation between the two levels of infinity, that the real numbers are more infinite than the natural numbers, but they have this very strange relation. In general, if we have a set, call it X, with n elements, you can form 2 to the power of n different subsets of that set. Let's just see how that works. We have the original set, in this case with 3 elements. You can now form a new set, which is the set of all the possible subsets. So you have a subset with nothing in it. You have 3 different subsets with 1 element. You have 3 different subsets with 2 elements. And then you have one where they are all 3. And clearly you can see that for each element, you can either have it in or not in. And therefore you have 2 to the power of n different possible subsets. In this case, you have 3 elements. So yeah, you get 2 to the power of 3 equal 8 different subsets. So what we've seen is that we have the same relation as we have between the continuum and the natural numbers. This is called the power set, the set of all possible subsets. And the real numbers are equinumerous with the power set of the natural numbers. That was one of Cantor's results. And then he started to speculate, could there be something in between? Something that's more infinite than the natural numbers, but less infinite than the real numbers. This is called Cantor's continuum hypothesis. He thought there wasn't, but he wasn't able to prove it. And it took quite a long time before that question was settled. And some people are still not happy with the way it is settled. You can also ask, well, how about a finite line? Shouldn't that be somewhere between the natural numbers and an infinite line? That's not true either. We ask, what is the cardinality of the set of points on a line of a finite length? But we can take such an example here and show that you can bring the points on a finite line into a one-to-one correspondence with the points on an infinite line. And the simple way of doing it is the tangent function. For each point between minus pi divided by 2 and plus pi divided by 2, you can map one to the other. And there's only one way of doing it. And you can take every point on the y-axis and map it to any point, to the corresponding point on the x-axis and vice versa. So in some sense, there's the same number of points on the finite line, which has a length of pi, and the infinite line. So the cardinalities of the finite interval and the infinite line are identical. Another surprise when you start to play with infinity. Now, Cantor's work was quite controversial when it came out, and Cantor was a bit of a strange person. I think today he would probably be diagnosed with bipolar disorder. And the hostility some people showed to his work certainly didn't help. One of his critics was a professor in Berlin, Leopold Kronecker. He stated that the dear God made the integers, everything else is made by humans. Then you take the Swedish professor with a German name. He had German ancestors, but he was still in Sweden. He founded a mathematical journal and was editor for a number of years. And he supported Cantor and published several of his papers. But even for him, Cantor was getting a bit heavy and getting a bit too philosophical. So he wrote to Cantor a comment on a paper Cantor submitted. And I'll try to rephrase it in English. It's something like, it may well be that you and your theories will not get the recognition they deserve in our lifetime. Basically, he wanted Cantor to withdraw the paper because this was getting too outrageous. Cantor obliged and never published in Acta Mathematica again. David Hilbert was the foremost German mathematician of the time in Göttingen, and he was an admirer of Cantor's work. Here's another quote. "From the paradise Cantor has made for us, nobody shall expel us." You may wonder why all these quotes are in German. And the reason is simply that the center of gravity for mathematics had moved from France in the early part of the 19th century to Germany in the second part. So really all the dominating mathematicians were Germans in that area, in that time. Whereas if you go to the early part of the 19th century, most of them were French, but the French had been left behind. Hilbert, yes, I mentioned Hilbert's Hotel, so let's take a look at Hilbert's Hotel. Hilbert's Hotel is a hotel with an infinite number of rooms, but they're all occupied. So what happens if one more person turns up and wants a room? Well, simple solution, you move everybody one step up. Problem solved. Next problem, an infinite number of new guests arrive. What do you do then? Well, you take the guests from room 1 and move them to room 2n. So everybody's moving up. The problem is it'll take a while because the corridor there is infinitely long. So is Hilbert Hotel profitable? Well, you might think that an infinitely big hotel with an infinite number of rooms all occupied would make an infinite profit. That is not necessarily the case because the resources required to build it would be infinite as well. You should perhaps look at the profit per room. If you have a net profit per room of even a penny per century, it would be infinitely profitable. However, if at any time there's only a finite number of guests, it would go bankrupt immediately. I mentioned Hilbert was known for his list of problems. He gave a presentation at a mathematics conference around the turn of the century. I mean, not the recent turn, but the previous one. And he listed a number of problems he thought that would be worthy working on for the next century. And he came up with 23 problems. The status now is that 8 of them have been completely cleared up and there's no disagreement. 8 are partly solved or they're solved, but not everybody's happy with the solution. 3 of them were a bit vaguely formulated. He wanted progress in a certain area, so you can never really say whether that's solved or not. You can always say, well, we want a bit more. That only leaves 4 unsolved, including the famous Riemann hypothesis, which is problem number 8. And problem number 1 in his list was the continuum hypothesis. Is there an infinity between the natural numbers and the real numbers? And his problem number 2 was that prove that the axioms of arithmetic are consistent. So if you do your math, you can never get a contradiction. I have tried to see if there was any particular order of his problems, but I haven't found any reference to that. I can't see any order myself. I just think he sort of noted them down as he thought about them. But it's interesting that the continuum hypothesis is top of the list. How significant it is, I'm not sure. It turns out there is a relation between these two. There are solutions, but they're not sort of regarded as the final word. So it's still work in progress in those two. And I think we should pause here for a drink and a convenient visit or whatever.
Okay.
10 minutes?
5, I think.
5 minutes, okay. 5 minutes, you can make a coffee.
Can I pose a question?
Yeah.
I think it's a simple question. Well, when you say status now, 8 solved and accepted, 8 partly solved, or solved but not universally accepted.
Yeah.
Thinking very simply, if something is solved, it is solved.
Yeah, but if you solve it by making some assumptions and not everybody's happy with the assumptions you have to make to solve it. Or if you, I also say,
completely solved.
Well, some are solved because you have solved special cases, but not the general case.
Yeah.
So it's not what I mean is that for 8 of them, it's not the final word. With the 8 first that are solved and accepted, that's clean and dusted. No more work is needed. That's done. Of course, you can start with those problems and invent some even more complicated problems from them. But as stated, they're cleared up. Whereas the next 8 there's some dust in the corner and not completely cleared up.
Is there any suspicion that Hilbert actually had the solution?
No. He probably tried his hand on a few of them and couldn't get it. I'm sure he would have tried his hand on the continuum hypothesis, and he would probably also try the Riemann hypothesis. So maybe it was, or some of them were just the things he liked to work on, but he hadn't made enough progress himself. So let's give it to the people and see if somebody else can make it.
Which poses the last question. Was he sanguine when he died?
Oh, Hilbert, yes. He died he died during the Second World War.
43.
Yeah. There is a story that during the early part of the war, maybe even before the war, but certainly after the Nazi takeover, he met up with a high-ranking Nazi, and this guy asked Hilbert, how is mathematics in Göttingen now you got rid of all the Jews? And Hilbert answered, there isn't any more mathematics in Göttingen because all the Jews had gone. So he was quite with it, and I think the Hilbert Hotel story was from a talk he gave in the 20s. Cantor is a different matter. He was in and out of sanatoria and so on. But he did receive a lot of recognition in his later years for his work. Although he was so, Kronecker was so hostile to him. Kronecker was professor in Berlin and prevented Cantor from ever getting a job in Berlin, which he wanted, but he didn't get it. And coming to the relations between mathematics and logic, and one of the prominent persons is Gottlob Frege, who published some doorstoppers, Basic Laws of Arithmetic, Volume 1 in 1893, and then he worked on for Volume 2 and published that 10 years later. And what he tried was to derive all the laws of arithmetic from logical axioms, really addressing Hilbert's second problem, to prove that arithmetic is consistent, that you can never, if you do it correctly, get any contradictions. As the second volume was going into print, he got a letter from Bertrand Russell. And that made him add an appendix. And I'll give it in English this time because it's a bit long. And it goes like, hardly anything more unfortunate can befall a scientific writer than to have one of the foundations of his edifice shaken after the work is finished. This was the position I was placed in by a letter of Mr. Bertrand Russell, just when the printing of this volume was nearing its completion. So just an innocent-looking question from Bertrand Russell prompted him to doubt all his 10 years of work. And what was it Russell wrote? Well, he raised the question, is the set of things X that are such that X is not a member of X itself, a member of X? It sounds very convoluted, so I'll give you an example. A soldier is ordered to shave all those members of the regiment who do not shave themselves. Question, should he shave himself? Because if he does, then he shaves himself and then he shouldn't. And if he doesn't, then he doesn't shave himself and then he should. So whatever he does, he'll get court-martialed for disobedience. And you can think about the nun who is asked to pray for all those nuns who do not pray for themselves. Well, whatever she does, she'll be excommunicated for disobedience. And you have similar logical problems in language. Is the following sentence true? This sentence is false. Well, if it's true, then it's false. And if it's false, then it's true. And if I say I'm a liar, am I then telling the truth? The basic problem in all these cases here is that of self-reference. And what Russell then wanted to do was to remove problems like this from math. And he went on to work together with Alfred North Whitehead to publish Principia Mathematica in 3 volumes, 1910 to 1913. And of course, the title was inspired by Newton's work, Philosophiae Naturalis Principia Mathematica. Russell wasn't one to be modest. It's over 2,000 pages of logic symbols. And this is just an extract here. And it's widely regarded as one of the most unreadable books ever published. And he thought that he cleared everything up. But before we go back to that, I just need to address this question here. What is an axiom? I've used the word a couple of times, so we may need some clarification. An axiom is an obvious or self-evident postulate that cannot be proven from more basic postulates. It's something that sounds absolutely obvious, but you can't prove it because it's so obvious that you can't prove it. But you can use the axioms for further reasoning and deduction and make derivations from them. For example, Euclid's geometry is based on 5 basic axioms. And the challenge is you want to have as few axioms as possible, and you want them to be as obvious as possible, and then build everything else from them. In set theory, there are what's called the ZF or the ZFC axioms, named after 2 mathematicians, Zermelo and Fraenkel. And there's 8 axioms, and the CFC, there's a 9th, what's called the axiom of choice. That's a bit of a technicality, I'll not go into that. There are alternatives, but the ZF or ZFC set of axioms is usually what mathematicians use if they work in basic math. So, for example, there is an axiom, the axiom of the empty set. Simply says that there exists a set that does not contain any elements. Well, sounds obvious, but you have to start somewhere. You have to have that as part of the fundamental. You can't prove it. It's just a statement. But it sounds obvious. In formal set theory language, that statement looks like this. So, yeah. Let's try to decipher that statement. Mathematicians, he would read it like this. There exists, that's this symbol here, a box, X, such that for all elements in the universe, Y, it is not true, that's the negation, that the element Y is contained in the box X. A non-mathematician would just say the box is empty. But in formal language, you have to use that expression there. That's one of the simplest axioms. Let's try a few more. There's the axiom of infinity, which states that there are sets with an infinite number of elements. Looks a bit more complicated, but it basically says that you can keep adding elements to a set. And that's the axiom of the power set, which says that for any set, you can form its power set, which is the set that contains all the possible subsets. It also looks a bit terrible. And some of the other axioms are far worse than this. They can't really be expressed in ordinary language. At least these three I've shown, they can be expressed in ordinary language.
If you can't express them, how can you understand them?
Well, you have to be a purist. It's the language of basic math. It is like learning a new language, and I'm not into all the details of it. But now we come to something a bit disconcerting, incompleteness. We have this chap here, Kurt Gödel, an Austrian who went to work at Princeton Institute for Advanced Study, and actually was a good friend of Einstein. And he published what was called the incompleteness theorems. And what he showed was that any axiomatic system that is powerful enough to describe the arithmetic of the natural numbers, such systems, you can make a couple of statements on them. And he proved that if a logical or axiomatic system is consistent, then it can't be complete. And what you mean by this is that there are truths that can never be proven. So sometimes a mathematician working on a problem that doesn't seem to be provable may think, maybe it's one of the Gödel cases here. That it's true, but I can't prove it. It may still be true. If it's false, then you should be able to find a counterexample, and therefore a false statement can always be proven false. But a true statement sometimes can't be proven true. And the second discovery he made was that the consistency of axioms cannot be proven within their own system. So if you have a set of axioms, you cannot use those axioms themselves to prove that the system is consistent and can never lead to contradictions. And this really upset the mathematicians a lot, because it means that mathematics isn't quite as solid as we might have liked. And it prompted the French mathematician Larrivee to come up with the statement, God exists because mathematics is consistent, and the devil exists because we can't prove it. Gödel went on to work on the continuum hypothesis. And he published a paper proving that the existence of a set with intermediate cardinality is unprovable in standard set theory. So it's one of the examples of a statement that may be true, but you can't prove it's true. You can add it as an additional axiom. And what it means is that the resulting theory will be consistent if and only if the initial system was consistent. Even worse, there was an American, Paul Cohen, proved that the non-existence of an intermediate set is also unprovable. And this means that the continuum hypothesis is an undecidable proposition, at least within standard set theory. You can never prove one way or the other. And there are other examples in set theory where we find undecidable propositions. Okay, let's go back to the numbers we normally work with, finite numbers. And sometimes we come across huge numbers. So some examples here. The Riemann hypothesis, again, it's been proven to be true for at least the first 10 to the 13 zeros of the zeta function. We don't know whether it's true for all the zeros, but at least up to 10 trillion, it's true. That's a big number. Here's a bigger one. The Goldbach conjecture is true up to at least 4 times 10 to the 18. What is the Goldbach conjecture? Anybody knows? The Goldbach conjecture states that every even number can be written as the sum of 2 primes. So, for example, 5 is equal to, we need an even number. 8 is equal to 3 plus 5. So take any even number you like, and you can decompose it into 2 primes. And that works at least up to 10 to the 18. You think that's a big number? Well, mathematicians have some bigger ones. There's something called the Mertens conjecture. I'll show you what it is later. It fails for some unknown number, but that number is no more than 10 to the power of 1.39 times 10 to the power of 64, which is a huge number. Later it has been reduced a bit, but let's just see what the Mertens conjecture is. First, we define the Mobius function, which is a bit of a strange one. It's 1 if n is square free, doesn't contain the same prime factor twice, and has an even number of prime factors. It's 0 if there's a square prime factor, and it's -1 if there's an odd number of prime factors. So if you map this, it looks like this. It alternates between 1, 0, and -1, and just fluctuates. And then we form the Mertens function, which is the sum of the first n values of the Mobius function. And that looks like this. And the Mertens conjecture states that this function here is bounded to the square root of n. Looks reasonable. But the interesting thing about it is that if this is true, then it follows that the Riemann hypothesis is also true. So this would have solved the Riemann hypothesis. In some sense, the Mertens conjecture is a stronger statement about the distribution of the primes than the Riemann hypothesis. Now, it turns out that the Mertens conjecture fails at some huge number. Doesn't mean that the Riemann hypothesis fails as well, because the Riemann hypothesis is weaker, so that could still be true. We don't know. But what was shown was that there is some number. We don't know it. We don't have an example, but it can't be more than 10 to the power of 6.91 times 10 to the power of 39, which is big. There's something called the Littlewood violation, and it was shown to occur, again, for a number that has to be smaller than some given number, That was 10 to the 10 to the 10 to the 34, which has now been reduced to 10 to the power of 316.
Good.
What is the Littlewood violation? Well, let's look at the primes. We have the prime counting function that enumerates the number of primes smaller than a given number. And we have something called a logarithmic integral, which is very close to the prime counting function. And it looks as if the prime counting function is always less than logarithmic integral. But Littlewood proved that there must be numbers, large numbers, where this is not true anymore, where the prime counting function actually exceeds the logarithmic integral. So he gave his student the task to find an upper limit for that smallest number. And this is what Buus came up with. There must be a number that cannot be bigger than this where this happens. And now it's been reduced, and it's strongly believed that this is the limit, that there's nothing below that. We know that it must occur before that number, and it probably occurs around that number. But it's beyond even the most powerful computer to look at the details. And all these numbers, they are big, but they're finite. They're simply in a different category from infinity. Not even near infinite. I hate the term near infinite. It's nonsense. You shouldn't use it, because there is no such thing as near infinite. Either it's finite or it's not. Now let's look at another example here of infinity. Let's assume we have an infinite universe that's sort of reasonably homogeneous. If you take a solar system that has, or a whole galaxy for that matter, that has a finite number of particles. And if each particle has a number of possible states, then the number of possible different galaxies or solar systems must be finite. It's huge, but it's finite. But if the universe is infinite, and there's a finite number of ways of making solar systems or galaxies, that means some of them must be identical. Actually, there must be an infinite number of identical galaxies. But that doesn't mean that any one of them has to be identical to ours. They could be a little bit different, and there could be an infinite number of galaxies that were slightly different from ours. But there must be an infinite number of identical galaxies in this case, if the universe were infinite. Okay, let's come to my last slide. Just some final comments and a couple of questions. Nearly all physicists and many, well, probably most mathematicians have used the concept of infinity without any major concerns, and usually you get away with it. No problem. It's a convenience. But it is, as you've seen, a slippery topic, and it does contain some surprises. And as you've seen also, there's a hierarchy of infinities. We can form power sets, and we can form power sets of power sets. So the hierarchy itself is infinite. What they mean, we don't know. Some questions here. Does the physical continuum actually exist? Or is space and time ultimately granular? Perhaps on the Planck scale, we don't know. Again, we use the continuum as a convenience. Do infinities exist as more than a mathematical concept than a physical convenience? Are infinities real? We will probably never find out. And the final question, is mathematics invented or discovered? If you take the Kronecker view, it's invented. God created the integers, and then we go on to invent everything else. If you take the Hilbert view, we start from some basic axioms, and then we discover the consequences. And I actually think it's both, because we can choose, we can discover, or we can invent the set of axioms we start from, and then we can look at the consequences and discover what they lead to. Okay. Any more questions?
An awful lot of these very clever chaps in the sort of late Victorian and early 20th century were doing very, very complicated mathematics without computers.
Yeah.
How did that work? I mean, we're so used to doing computers.
Yeah, because they were working on basic concepts. They were proving things, but computers have come in even to pure maths. For example, the Mertens conjecture, that work required huge amount of computing. They started from some other mathematical work to use that to prove this falseness of the Mertens conjecture. They had to know the zeros of the Riemann zeta function to about 100 decimal places. Completely impossible without the use of computers. The four-color theorem was one of the first examples where a fairly deep mathematical question was solved by computers. And a lot of the work on also the Littlewood violations has used computers. Now, Littlewood's work himself was done with paper and pen. He just proved the existence. He wasn't able to set any limit, but he showed that this must happen sometime. So it's different kind of questions, perhaps, and they require different tools. But
must have been a huge leap in things as soon as computers.
Yeah, there was certainly the four-color theorem. I think that was about 1976, and there was hostility against that proof because it relied on computers. I believe that more efficient computer programs have been written since to address the same problem and solve it in simpler ways. But it was, I believe it was 1,100 hours of mainframe computing time. Princeton Institute of Advanced Study didn't have computers for a long time. They do now. There's a limit to how far you can go by pure reasoning.
Yes.
Yes. Has any axiom ever been shown to be wrong?
Not to my knowledge, because I think they're so basic that if there is something wrong with them, it would be obvious. But there are cases where they've been dropped. For example, go back to Euclid again, his parallel axiom that if you have a line and a point, you can draw one line through that point that's parallel with the original line. That's what it says. But you can do geometry without that assumption, but then you do geometry on curved surfaces. So you generalize geometry by dropping an axiom using fewer axioms. And Riemann was involved in that, going back to this chap. He's one of the really big guys in math.
And in hotel.
Yes.
So I'm thinking, going back to the statement, I know this is true, but I can't prove it, and it cannot be proved.
Yeah.
So has there ever been the case where actually eventually somebody did show that it wasn't?
Not to my knowledge. Not to my knowledge. It's possible. I mean, people thought that maybe Fermat's last theorem belonged to this group of true statements that cannot be proven true, but that was proven true eventually. It's been true all the time. We just didn't know whether it was true or not. But I'm not aware of sort of obvious statements that have later been shown to be false. There are examples of other groups of axioms that try to plug some of the holes. And I think you can get some of the pure mathematicians in a heated argument on what is the best set of axioms to use, and but they become, I can't get my head around some of them. They look much more complicated than the few ones I showed.
Well, if you can't, I'll take that.
Yeah. Is there, I don't know if there are any questions that Dave's end.
Questions from the laptop.
On the laptop, yeah. Dave? Might have to ask
On
Dave,
mute, you can ask Jens a question.
The few who have survived so far.
Well,
A question on the invented or discovered. So I guess we invent ways of representing things, but what we represent are things that are discovered. Like Fermat's last theorem discovered a solution to it.
Yeah.
It was there all along.
It was there, we just didn't know. But I mean, I would say we invent the starting point. We decide where we want to start from, and then the rest should follow. So
some branches of mathematics are invented, aren't they?
Yes, yes.
Well, specifically to try and prove something. But as you say, it might have been there all the time. But by inventing this, we've discovered it. We hence believe in both. Amazing.
yeah.
I just want to know who it was that was having a show.
Right. Well, well
Yes,
done,
that's a don't do it now.
Right. Let's have a quick word with the team.
Brilliant.
Well, I hope you enjoyed that. It certainly stretched me, but there were lots of interesting questions and answers from Jens. So I was obviously somebody who can grasp this subject rather better than me, who can only add 2 and 3 together and get, well, the wrong answer. Anyway, so a very well put together presentation as always with Jens, and I look forward to any further developments in that direction in due course, Jens. But we'll close the meeting tonight and look forward to seeing you either Zoom or perhaps a small number in the rooms on the 12th of July. And thank you, Dave, for hosting it, and we'll see you all in the near future.
Thanks,
Thanks, Jens. Thank you.
Jens.
Cheers, folks.
A brilliant talk.
I wish I understood it.
Well done, Jens.
Absolutely brilliant.
Bye, folks.
Fantastic. I see you've moved, Dave.
Sorry?
You've moved, obviously.
I have, yeah, to the surface of the moon. Yeah.
Yeah.
See you tomorrow night.
Bye then, folks. Yeah. Bye then.